there.
Let's see. My name is Brandon Dodd. I did the administration cooling tower. I did the experimentation with Bradley. Okay, now in our report, we'll go over some of the theory behind cooling towers, talk about the measurements and experimental data that we gathered from the cooling towers, perform some calculations of mass and energy balance for the system. We'll show you the results of the calculations, summary, conclusions, and recommendations for further experimentation. Okay, theory of the cooling tower. The cooling tower, it operates by having airflow going into the system, and that comes in contact with warm water running through the system, and this causes some of the water to evaporate, which changes the enthalpy properties of the air. And the evaporation of the water, energy is provided from the evaporation of water from the heat of the water, so you basically get a net energy change to the system. There's a fan at top which pushes the air out. As you can see by my arrows, I weighted it by the velocity profile. The velocity air coming out the center of the fan and on the outsides of the fan is much less than the velocity coming out through the center radial positions of the fan. Here's a picture of the cooling towers. On the left, you have the cooling tower intake. This is where air goes into the system. And on the right, you have the exhaust. And then this fan had a circular profile. So, equipment that we use to take measurements across the fan, we use the X-Tech 1-inch digital anemometer, and we also used 4-inch non-digital anemometers. We also used X-Tech digital temperature and humidity sensors. These sensors were set to record temperature and humidity data every 2 seconds. Equipment we did show, we used a stopwatch. You had to use a stopwatch for your 4-inch anemometer because it just shows you feet. It doesn't have a time rate to it, so you have to have a way to calculate time. We also use duct tape and wire so we could place the X-Tech sensors. When taking our measurements on locations 1, 2 on the intake is where we place our X-Tech sensors, and we place it on location 3 on the exhaust. We took fluid velocity measurements at locations R1 through R5, starting with R1. This is what the data look like for the velocity from R1 to R5. As you can see, as you get to the center line of the fan, the velocity drops off, and as you get to the outer wall, the velocity drops off. The velocity is actually highest in between the center of the fan and the outside wall. And it's got a parabolic relationship. The X-Tech sensors on the intake versus the exhaust, you can see that there's a temperature difference there. The exhaust fans, on average, about 2.5 degrees Celsius warmer than the intake. The X-Tech sensors did have some uncertainty to them, which is shown by the air bars, and in comparison to the intake, it's actually pretty substantial. As far as humidity goes, like I said, the unsaturated fluid is evaporating water as it contacts warm water. So the outflow humidity is higher than the inflow humidity. And this is important because it changes your enthalpy properties. One of the challenges of this is actually doing the mass balances and trying to determine your airflow rate through the system. Airflow rate is equal to the density of the air times the volumetric flow rate. And we did all the calculations in metric. And to calculate the volumetric airflow rate, you can take the volumetric flow rate equals 2 pi, and then you can integrate the velocity at a given radius times the radius in respect to VR. And to do this, if you plot VR versus R, and you can take the area of the curve, which is a simple way of calculating the integral. When you multiply that times 2 pi, we calculated the volumetric flow rate to be 16.3 approximately meters cubed per second. I don't have an equation type there. To calculate the mass of dry air, there's several ways you can do it. You can use ideal gas laws. What I did is I actually used a psychrometric chart because I calculated the volumetric flow rate, and the psychrometric chart has values on it for the specific volume of dry air. So I used the specific volume of dry air I calculated at the exit. I calculated my mass of dry air to be 20.2 kilograms per second. Here's a psychrometric chart. 0.0 is where I calculated my specific volume of dry air, and you can see the purple lines go over to the change in absolute humidity. That change in absolute humidity is H2O gained by evaporation. And you can see my enthalpy in and enthalpy out values. That change right there is the heat absorbed from the cooling water. I use a psychrometric chart for most of my major calculations to simplify things. To find HV, you use a steam table. I picked the value at temperature equals 25 degrees Celsius because that's approximately the temperature of the system when we're analyzing it. And I average that to be 2,400 kilojoules per kilojoule, or kilojoules per kilogram water. And that's my results. I get my delta Q equals the mass of the air out times the enthalpy of the air out minus the mass of the air in times the enthalpy of the air in times the change in the mass flow rate of water times the specific, the latent heat of water. And so I calculated my heat flow through the system as 876 kilojoules per second. And to convert that, 876 kilojoules per second equals approximately 3 million BTUs per hour, which comes out to be around 250 tons of coolant. And that was the calculated energy change of the administration cooling tower during experimentation. Conclusion recommendations. Since we only collected exhaust temperatures at one location along the radius of the fan, that doesn't show how the temperature is affected by the flow rate across the radius, because the velocity profile does change. So I'd recommend taking more temperature measurements across the radius of the fan. And then we only took velocity measurements across one angle, so we might want to try other angles relative to north. And relevance to chemical engineering. This is a good example how properties can affect engineering process. The mass balances and the energy balances system, the thermodynamic properties of water all influence how the cooling tower behaves and how effective it is. That's it.